Hello students, welcome to aimsindia online classes. This is a chemistry session. Here we are discussing about the chapter atomic structure. In this session, we are going to see about electromagnetic radiation. Electromagnetic radiation, or just simply it is called EMR. It is a form of energy that is produced by the moment or oscillation of electrically charged particles which are traveling through either matter or vacuum. So, the electrically charged particles, while traveling through the matter or vacuum, they create some moment or oscillation. Because of this moment and oscillation, energy is being emitted by those particles. So, that emitted energy comes out in the form of this electromagnetic radiation. Actually, these electromagnetic radiation do not need any medium for their propagation. Means they can travel through the matter and even they can travel through vacuum also. They do not need any medium for their propagation. They can travel through the both, through the matter as well as through the vacuum. See here, some examples for the radio electromagnetic radiations are given, like visible light. The light which we see is one of the forms of electromagnetic radiations. Ultraviolet radiation, infrared radiation, X-rays, gamma rays, these all will come under electromagnetic radiations. These are produced from the electrically charged particles while they are moving with the high velocity. Okay. Characteristics of this electromagnetic radiation. Electromagnetic radiation is released as a photon. Yes, we know energy is emitted in the form of small packets. Each packet of energy is called a photon. This we study from the Planck's quantum theory. He states that there energy emitted by the particles is not emitted continuously. This is emitted discontinuously in the form of small packets. These packets of energy are called photons or quanta. So these electromagnetic radiations also released from the particles. So this also will be in the form of photons. So which are bundles of light energy that travel at the speed of light. So these bundles of energy are also will be traveling with the speed of normal light. That is 3 into 10 to the power of 8 meters per second velocity. So these all electromagnetic radiations are said to be having the same velocity just like the light radiation. Electromagnetic radiation can travel through even empty space also. Yes, we said here, electromagnetic radiations do not need any medium for their propagation. That means they can travel through the medium, and even they can travel through even vacuum also, empty space also. But most of the other types of waves must travel through some sort of substance. For example, sound waves. The sound waves need either a gas, solid, or liquid to pass through in order to be heard. Isn't it? Sound waves need a certain medium, either gas, solid, or liquid. Something matter should be there to be passed, and then only we can hear the sound. So to pass through for the sound waves, there should be, or it is needed must a medium, any one of the states. But for electromagnetic radiations, no medium is needed. They can travel through even empty space or vacuum also. Okay. So an electromagnetic radiation is always characterized by certain properties. So each and every electromagnetic radiation is characterized by some properties. Let us see those properties here one by one. First among them is wavelength. It is defined as the distance between the two nearest crests or nearest troughs is called the wavelength of that wave. What is this? The distance between the two nearest crests or troughs of a wave is called the wavelength of that wave. It is denoted with the symbol lambda. So this symbol is pronounced as lambda and is measured in terms of centimeters, millimeters, angstroms, micrometers, nanometers. These all are the units of this wavelength. Why? Because we are telling this is a distance. So whatever the units we say for distance, all will come as units for wavelength also. But it is a micro quantity. Generally, most probable preferable units for the wavelength are angstroms. And even we can use centimeters, millimeters, micrometers, even nanometers also. Suppose this is a wave. So waves we know like this they will be. The higher altitude is called crest, the depth is called trough. The distance between the two nearest crests or the distance between the two nearest troughs of a wave is called its wavelength. Suppose this is a crest and this is a crest. The distance between these two nearest crests is called as wavelength of this wave. The same can be defined in other way also. The distance between the two nearest troughs, the distance between these two is called a trough, a wavelength. So this and this both are defined as wavelength of that wave. So a wavelength contains a complete wave with one crest and trough we can say. So if you see from here till here, this one complete wave you can say. So the distance for the complete wave also can be taken as a wavelength of that radiation. So wavelength is denoted with the symbol lambda and it is measured in terms of centimeters, millimeters, micrometers, nanometers. Mostly used units are angstroms. We know 1 angstrom is equal to 10 to the power of minus 10 meters or 10 to the power of minus 8 centimeters. Okay. Next, one micro, some other units conversations also given here. 1 micrometer is equal to 10 to the power of minus 6 meters and 1 nanometer is equal to 10 to the power of minus 9 meters. So whatever the units based upon the calculation purpose, you can convert them from one unit to another unit. Okay, wavelength is the distance between the two nearest crests or two nearest troughs of a wave is called the wavelength. It is denoted with the symbol lambda. Okay. Next one, frequency. Frequency is defined as the number of waves which pass through a point per second or the number of waves passing through a point in 1 second is called as frequency of that radiation. So a radiation will be moving or propagating in the form of wave. While moving like that, in the path of wave, if we keep a point, if we count the number of waves passing through the point per second, that number of waves passing through a point per second or in 1 second is called its a frequency. The number of waves passing through a point per second is called its frequency. The same can be defined in other ways also. The number of oscillations, the number of revolutions, they all will come under frequency. So as we are telling, it is denoted by the symbol nu. So this symbol is pronounced as nu. Frequency is denoted with the symbol nu and is measured in terms of cycles per second. That means number of waves per second. So simply you can say per second. Second inverse is a unit of frequency. The other unit for frequency is a hertz. So hertz and second inverse are the units of frequency. Simply we can say one more unit, cycles per second, oscillations per second. These all will come under simply per second. Okay, second inverse or hertz are the units of frequency. Frequency is inversely proportional to wavelength. Yes, frequency is inversely proportional to wavelength. What did we say wavelength means? The distance between the two nearest crests or troughs of a wave. We call as wavelength. So if wavelength is greater, then the number of waves passing through a point per second will be less because its wavelength is greater. So frequency will be less. If the wavelength is very smaller, then number of waves passing through a point per second will be much greater. So its frequency will be greater. We are telling as these all electromagnetic radiations will travel with the same speed. So if wavelength is greater, frequency will be less. If wavelength is smaller, frequency will be greater. So we can say here frequency and wavelength are inversely proportional to one another. It can be represented mathematically like this. Nu is directly proportional to 1 by lambda. So to remove the proportionality, you can keep a constant. By that it becomes nu is equal to c by lambda, where c is a constant which is equal to velocity of light. So we know the velocity of light is equal to 3 into 10 to the power of 8 meters per second. Thus, a wave of higher frequency has a shorter wavelength, while a wave of lower frequency has a longer wavelength. Isn't it? We're telling here wavelength and frequency are inversely proportional one to another. So, if the wave if it is having a longer wavelength, it will be having less frequency. If a wave it is having the shorter wavelength, then it will be having higher frequency. The longer wavelength waves, such as radio waves, carry low energy. Yes, wavelength is also inversely proportional to energy, because we know energy is directly proportional to frequency. So if frequency is greater, energy also will be greater. If frequency is lower, energy also will be lower. Now, the waves with a longer wavelength will have lower energy, such as radio waves. So radio waves are having greater wavelength. That is why these will be having less energy. They carry low energy. That's why we can listen to the radio without any harmful consequences. Isn't it? We listen to the radio, to music and news. So we're able to listen to that without any harm. Because of that, these radio waves carry very less energy which won't harm us, because the radio waves wavelength is much longer. Another way, shorter wavelength waves, such as X-rays, carry higher energy. So X-rays are having shorter wavelengths. If wavelength is shorter, then frequency and energy will be higher for those. So these X-rays carry higher energy that can be hazardous to our health. It may be dangerous to our health. It may cause harm to us. That is why lead aprons are worn to protect our bodies from harmful X radiations when we undergo X-rays. So we protect our body from these harmful X-rays when we undergo X-rays with some lead aprons, because these X-rays are carrying much higher energy which may harm us, because their wavelength is very shorter. Okay, in this way the radiations with the longer wavelength are carrying less energy, and the radiations with the shorter wavelengths will carry much greater energy. So here they are compared here. If you see this wave, it is having very shorter wavelength. As the wavelength is shorter, they have high frequency as well as high energy. Like X-rays, gamma rays, these will be having low wavelength and a high energy as well as high frequency. And some other waves with a longer wavelength, they will be carrying low frequency or low energy also, like radio waves. Their wavelength will be greater, so energy and frequency will be lower for them. They won't cause much harm to us. Okay. Frequency and wavelengths of different electromagnetic radiations are shown in the chart form here. See that? Yes, if you see, radio waves are having wavelength around 10 to the power of 3 meters in units meter they have given. So their frequency is less. Wavelength is greater, so frequency is less here in H. Whereas if you see X-rays or gamma rays, The wavelength of X-rays is given 10 to the power of minus 10 meters. It is very smaller when compared to the radio waves wavelength. So then their frequency or energy is much higher. See, for the radio waves and gamma rays, wavelength is being very shorter. So they are carrying high energy and even high frequency too. So both are inversely proportional one to another. So as we can observe from this chart here, as wavelength decreasing, frequency increased. Okay. Next one, wave number. It is simply the reciprocal of wavelength. So the reciprocal of wavelength can be defined as wave number. To say definitionally, it is the number of wavelengths per unit length. That is, the number of wavelengths per centimeter or per unit length is called wave number. Wave number is simply the reciprocal of wavelength or inverse of wavelength is called as wave number. So this is denoted with the symbol nu bar. We know nu is denoted to represent frequency. Nu bar is representing wave number. Wave number is denoted with the symbol nu bar. It is expressed in centimeter inverse or meter inverse because the units for wavelength are taken as centimeters or meters, etc. So the reciprocals of these units are used for the wave number units. So units of wave number will be reciprocal units of wavelength. For the wavelength we have used the centimeters, meters, angstroms, this all. Now the units of wave number will be reciprocals of those like a centimeter inverse, meter inverse, angstrom inverse and so on. Okay, mathematically it can be represented like this. Nu bar is equal to 1 by lambda, where lambda is the wavelength of electromagnetic radiation. If we know wavelength, we can calculate its wave number. Okay. Next one, amplitude. Amplitude is defined as the height of the crest or depth of the trough of a wave. The height of a crest or the depth of the trough is known as its amplitude, the amplitude of the radiation. It is denoted with the symbol A. It determines the intensity of the radiation. As the height of the crest or depth of the trough increases, the intensity of the electromagnetic radiation increases. So it gives information about the intensity of the radiation. As the height of the crest or depth of the trough increases, the intensity of the radiation increases, vice versa. See here, suppose if it is a wave, the height of this crust is nothing but its amplitude. At the same time, the depth of the trough also the same amplitude. It is considered as amplitude of the wave. If this depth increases, intensity of the radiation increases. If it decreases, intensity of the radiation decreases. Okay, this is about amplitude. Amplitude is defined as the height of the crust or depth of the trough of a wave. Okay, next, velocity of electromagnetic radiations. It is defined as, generally the definition for velocity we know, the distance covered in 1 second or the distance covered in unit time is called velocity. The same we can say for the electromagnetic radiations also. So the velocity of electromagnetic radiations is defined as the distance covered by that radiation in 1 second. It is denoted with the letter C. So here all the electromagnetic radiations travel with the same velocity, that is velocity of light. All the electromagnetic radiations travel with the velocity of with the same velocity, that is equal to velocity of light. What is the velocity of light? We know as it is 3 into 10 to the power of 8 meters per second or 3 into 10 to the power of 10 centimeters per second. So the distance traveled in 1 second by the radiation is equal to C is equal to lambda into nu. That is equal to 3 into 10 to the power of 10 centimeters per second, or 3 into 10 to the power of 8 meters per second. Okay, here this is a velocity of light. So earlier we have seen between the in the equation which is relating wavelength and frequency, that is nu is equal to c by lambda, because nu is inversely proportional to lambda. To remove the proportionality we have taken a constant c there. So from this equation, if you write c is equal to, this lambda will come this side, it becomes lambda into frequency, that is taken here. So which is equal to the velocity of light, that is 3 into 10 to the power of 8 meters per second. All the electromagnetic radiations are supposed to be traveling with the same velocity, that is 3 into 10 to the power of 10 centimeters per second, or 10 to the power of 8 meters per second. Okay, next one, time period. The time taken by the wave for one complete cycle, or one complete oscillation, or for one complete vibration is called time period. What is that? The time taken by the electromagnetic wave for complete cycle, or one complete vibration, or you can say the one complete oscillation is called time period. It is denoted with the symbol T. So as we are telling, this is the time taken for one complete oscillation. You can say units will be seconds. We say the number of the time taken for the one complete wave is called time period. So the time it is just a time. So what are the units for the time? Generally seconds. Seconds per cycle, or seconds per oscillation, or seconds per vibration, we can say. Simply we can say seconds. So here, suppose this is a wave. If we keep a point here, to pass through this point, the time taken by one complete wave to pass through this point is called its time period. The time taken for the one complete wave to pass through it, or the time taken for the one complete cycle. This we can say one cycle or one complete wave. For this wave, the time taken to pass through this point for completely is called its a time period, that is mentioned in terms of seconds. This time period is denoted with the symbol T. So here it is mentioned here also. In this way also, from one crest to another crest. So if we keep a point here at one crest, the time taken for this wave to cross this point through one another crest is its time period. Okay, in the same way, in terms of trough also we can say. Okay, that is a good time period. Next one, the arrangement of various types of electromagnetic radiations in the order of their either increasing or decreasing order of wavelengths or frequencies is known as electromagnetic spectrum. What is this? Whatever the electromagnetic radiations are there, if you observe them and if you arrange them in the increasing order of their frequencies or wavelengths, or in the decreasing order of their wavelengths or frequencies, then there's a chart which is representing all kinds of electromagnetic radiations is known as electromagnetic spectrum. Let us see here the chart once. See, all kinds of electromagnetic radiations are represented here: radio waves, microwaves, infrared light, visible light. So this is the light which we can see with our naked eye. This all cannot be seen. Ultraviolet radiation, X-rays, gamma rays. So out of these, all the, if you observe, all the electromagnetic radiations are arranged in their decreasing order of wavelengths, isn't it? Radio waves are having greater wavelength, whereas if you see these X-rays and gamma rays are having lower wavelengths. The same we can say in the other way also. These are arranged in their increasing order of frequencies. Because if wavelength is greater, frequency will be shorter. If wavelength is shorter, wave frequency will be greater. Both are inversely proportional, no? So we can say this chart as increasing order of frequency or decreasing order of wavelength. Out of this, the radiations which are after this visible radiation, they are having greater energy and a lower wavelength. These are radiations which can cause harm to us. These are hazardous radiations. So we should not be exposed to these radiations. They may cause damage to our body. So these radiations with a lower frequency or greater wavelengths, they do not cause any harm to us. That is why, as we told at the earlier, we can listen to the radio without any harm, because those radio waves are having a longer wavelength but lower energies. So this chart is called, which is representing all kinds of electromagnetic radiations with different wavelengths. When these all arranged in the increasing order or decreasing order of their wavelengths or frequencies is called electromagnetic spectrum. Okay, this is about electromagnetic radiations and their characteristics. Okay, thank you for watching our video. Please subscribe our YouTube channel Aims Today for latest updates and recorded videos.